So it is really a great pleasure for me to give a talk today to talk about some of my recent research projects on statistics-powered AI. So let me start by just giving you like a brief review of the history of AI. As you guys all probably know, like the concept of AI is not new. It begins at like 1950, and that time like we have the famous Turing test, and then afterwards we have like the first Dartmouth conference, which officially names AI as a research project. And then from 1960 to 1970, so that's the early development of AI. And at that time, they are mainly like rule-based and symbolic. So researchers tend to use like a number of rules to represent the complex word. So just to give you an example, so suppose if I have fever, if I have like a high temperature, then I might get a fever. So it's basically like these rules. But you can imagine that if we want to use such rules to represent the complex word, we might need like billions or even much more rules. So that's not feasible at all. And because of that, this leads to like what we call AI winter starting from 1980. And then 10 years later, so AI is about to revive. And at that time, like a fundamental change is to shift from those like rule-based AI that was developed earlier to data-driven analysis, which is basically machine learning. And that's also closely related to the rise of statistics at that time, which is data-driven in nature. And we all know that early like AI tools such as support vector machines and kernel methods, they have like they are deeply rooted in statistics. They have rigorous like statistical guarantees. And then starting from 2010, that's the area of deep learning and deep reinforcement learning. And finally, that's where we are now. We have entered an era of generative AI. So if you think about the history, so it only takes like 70 years from where the concept of AI was born to until what we are right now, where AI has been deeply integrated into our daily life. So it's really amazing. And now we have definitely entered an era of large language models and its derivatives. So this figure shows you like the speed at which these AI tools have been developing. So if you look at the upper panel shows you like the last year, the year of 2024, like for each month, how many large language models, how many major large language models were released. So by saying major language models, we mean models such as like DeepSeek or ChatGPT, etc. And you can see that every month they were like roughly on average like 20 models being released, which means that every 3 days we will have like 2 major large language models being invented. And if you look at the bottom panel, so the numbers are even more, much more crazy. So these numbers shows you like for each month, like how many derivative models which are built upon those major large language models that are either smaller in scale or they are being fine-tuned for some specific purposes, or being released or uploaded to Hugging Face. So each month they were like roughly 10,000 models being released. And this year, so those large language models, they are still being updated, they are still being developed. So just to give you 2 examples about the progress. So a few months ago, as you guys all probably know, the Google's large language model Gemini is able to win the gold medal in international mathematical Olympics. And the second example is more closely related to our academic. So basically, the DeepSeek RLHF model has been published in Nature, and the Nature editorial encourage you guys to bring your own large language models to the journal. So going back to today's talk, so in today's talk, I will discuss the title of my talk is Statistics-Powered AI. So basically, I will discuss 2 of my recent papers. Both are new rich papers, and I will talk about like how statistical tools can possibly empower those AI models such as large language models. So the first project that I'm going to talk about is an algorithm which we developed named DRPO, which is short for doubly robust alignment for large language models. So firstly, just to briefly introduce some background on how to train those large language models. So I know you guys must be very familiar with the procedure, so I will be as quick as possible. So basically, the training of those large language models, they takes like 2 steps. So the first step is the pre-training step. So basically, what we did is that we use like all those massive text available on the internet to train a transformer model. And that's typically achieved through the process autoregressive next token prediction. So essentially, what we do is that given each sentence, we divide those sentences into like a sequence of tokens. And here, each token can be either like a word or subword or a punctuation. And then we use like the first token to predict the second, and then the first 2 tokens to predict the third, so on and so forth. Okay? And by the way, this is like a famous quote from the Avengers movie series. So if you have watched the 4th series of Avengers, that's a famous quote from Iron Man. And after those large language models have been pre-trained, so typically we will not directly use those pre-trained models for deployment. So this is because after pre-training, although those models they are able to mimic human beings, they can speak our language, but they are not aware, for instance, whether their output is correct or not, whether the output is beneficial or helpful to our human needs. And because of that, to really deploy those large LLMs in practice, we need to have like another post-training stage. And there are 2 typical post-training algorithms available. So the first one is supervised fine-tuning. The other one is reinforcement from human feedback. So basically, for supervised fine-tuning, what we did is that we prepare like a high-quality data of the questions and the human answers. And then what we did is that we fine-tune the parameters in those large language models to ensure that their output should align with like these high-quality human answers provided in the data sets. So that's supervised fine-tuning. And in the first part of the talk, I will talk about my first paper, which is basically related to the second post-training paradigm gen. That is about reinforcement learning from human feedback. So essentially, reinforcement learning from human feedback is to use like reinforcement learning tools to fine-tune those large language models to align with human feedback. And as we all know, due to the breakthroughs of those reinforcement learning algorithms in the applications of video games, of the Game of Go and the large language models. So last year's Turing Award was given to Andrew Barton and Richard Sutton. So both can be viewed as the father of reinforcement learning. So they made a huge contributions to the theoretical foundations of reinforcement learning. So just to briefly give you a very good introduction of reinforcement learning. So in reinforcement learning, we are concerned with what we refer to as those sequential decision-making problems. So essentially, we assume that it is an agent that tries to learn and interact with a given environment. So at each time point, the agent will observe some features from the environment, summarized into a state vector SP. And then after observing those features, the agent can choose some actions, which we denoted as AT. And then the environment will provide some feedback to the agent, which is summarized into a numerical reward. And the agent keeps interacting with the environment at each time point. So at the end, you can imagine that the agent will receive like a sequence of the rewards. So the objective in reinforcement learning is just try to identify an optimal policy to maximize the cumulative reward that the agent receives in a long run. And in the first part of my talk, we will focus on reinforcement learning from human feedback. So just to give you like the 2 important references about this topic. So both are new papers. So the first paper is the 2017, I think, reinforcement learning from human preference paper written by OpenAI and DeepMind. So in this paper, they, to my knowledge, they give like the first introduction to deep RLHF. But in this paper, they didn't apply the methodology to like language tasks. So they applied the methodology to non-language tasks such as like video games or robotics. And then 5 years ago, this is like the famous instructed GT paper, which is the first successful application of RLHF to fine-tuning those large language models. Now, just to give you some background about how to conduct RLHF in LLMs. So if you think about in the application of LLMs, so the setting is slightly different from the classical reinforcement learning setting. And so if you think about the applications to LLMs, so we have the state, which is the question posed by the users. And we also have the actions, which corresponds to the output of those large language models. But the problem is that we don't have a natural reward in this setting. So if we want to have the reward, so this means that we need to ask like a human expert to give like a numerical score to indicate the goodness of like the output of the large language models. But as mentioned by the boy on the right, so providing like a numerical score for each output of the large language models can be very difficult. So suppose if for a given response, the expert gives like a score of 60. So that's very subjective. So why 60? Why not 70? Or why not 50? So that's very subjective. So what RLHF does is that instead of asking the human expert to directly give a numerical score, it asks the human experts to compare two answers and tell like which one is better. And this is much easier than directly giving the absolute scores. So to summarize, so that's the procedure being employed in RLHF. So essentially, for each question, we will ask like either human beings or like the LLMs to provide like two responses. And then we will pass those two responses to a human expert to indicate their preference. So among those two responses, which one is best? And then typically we will impose like a preference model to model those human preference data. And the most widely used model is like the Bradley Harry model. So indeed, this is a paper published in Biometric, which is a top statistical journal. And this paper gets like lots of citations in the recent years due to the popularity in conducting research with some LLM environment. So if you look at this formula, so essentially it assumes that for each of the response, there is like a reward function. And the probability of one response is being favored over another depends on the difference between the two rewards. So if a response has a higher reward, then it has a higher chance to be preferred. So that's the interpretation of this big model. And after we have such model, we basically apply like a maximum likelihood estimation to estimate the reward function. And once we have the estimated reward, then we can directly apply reinforcement learning algorithms to fine-tune those. Yes.
Function sigma is a genetic function here.
So typically it's like the sigma function. But there were like other general variations which use like hinge laws, for instance. There were other generations, but typically we will use sigma. Any other questions at this stage? Yes.
One question which I would like to ask, in this case, we're not looking at the discounted rewards, so essentially it becomes a bit of a bandit setting.
That's a very good question. So here, yes, like it's very similar to bandit setting. But if you look at the actual implementation of like some RLHF algorithms such as PPO, they still consider it as they still formulate the problem into an MDP.
Yeah.
So they optimize. Yes.
Well, the main question, what I'm getting at, is that what would be the use of reinforcement learning in this case compared to the bandit objective?
I would say here, like you can either use like a bandit objective or like NDP formulation to solve the problem. So there are algorithms developed for each type. So basically, it depends on how you model the problem, but both should be applicable here.
Thank you very much.
Thank you for the question. Any other questions? So to summarize, that's basically yields like the first type of baseline algorithms, which we refer to as PPO-based approach. So essentially, as what I mentioned earlier, so the idea is that given a set of questions, then we ask, for each of the questions, we provide two answers, and then we pass those two answers to a human expert to get the latest. And then we use the BT model and apply maximum likelihood estimation to estimate the reward. And once we have the reward, we apply like reinforcement learning algorithms, and typically it is like a PPO algorithm or its variants to update the optimal cost. So that's the first type of RLHF algorithms. So the second type of algorithms is referred to as like a DPO-based approach. So here, DPO is short for direct preference optimization. So if you look at the figure on the left, so this gives you like the first type of baseline algorithms that I have just mentioned. So as you recall, the first type of algorithms is like a two-step procedure. So essentially, we first estimate the reward model based on the preference data. And then once we have the reward, we can directly apply reinforcement learning algorithms to update to estimate the output. Okay, so that's the two-step procedure. That's the first type of baseline algorithms that I have just mentioned. Now, if you look at the figure on the right, so that's DPO. So the major difference compared to the first type of baseline algorithm is that the DPO is like one-step algorithm. Okay? So given the human preference data, it directly applies maximum likelihood estimation to estimate the output in one step. Okay? So why it can do that? So the idea lies in that if in the paper they found that the reward function can be basically derived in closed form using the optimal cost. So basically, if you look at this formula, so that's the reward function. And we can express the reward function using the optimal cost, so which is denoted by pi star here. And because of that, there's no need to first estimate the reward and then apply reinforcement learning algorithms to estimate the optimal cost. We can directly parameterize the reward function using the optimal cost, and then solve the optimal cost in one step using the maximum likelihood estimation. So that's the basic idea of DPO. And then like after its introduction, there were like various variants of DPO type algorithms, and we refer to those algorithms as DPO-based approach. So now I have introduced like two types of RLHF algorithms, but both algorithms they have some limitations. So essentially, first, both two algorithms they rely on the BT model assumption. So which which is like this model assumption to model human preference. And in the literature, people have studied, there were like many papers which suggested that the BT model assumption can be violated in practice. So for instance, one underlying assumption under the BT model is the transitivity assumption. So basically, suppose we have given a question, suppose we have like three answers. So if the first answer is preferred over the second answer, and if the second answer is preferred over the third answer, then under the BT model assumption, it implies that the first answer must be preferred over the first answer must be preferred over the third answer. So that's what transitivity means. But in practice, people found out that it is likely to have a circle. It is likely that for instance, the first answer can be preferred over the second, and the second answer can be preferred over the third, but the third answer may be preferred over the first. So there can be a cycle. And in that case, the BT model assumption will be violated. Now, even if the BT model assumption is correct, so the first type of baseline algorithms, those PPO-based algorithms, they are highly sensitive to the specification of the reward model. So if the reward model is misspecified, then the optimal cost might not be good. And for instance, it can lead to like a reward action in the according to the literature. And for the second type class of baseline algorithms, for those DPO-based algorithms, they are highly sensitive to the specification of the reference policy. So if the reference policy is specified incorrectly, then the optimal policy might not be very accurate. So if you go back to if I go back to this slide, so basically you can see that when DPO try to express the reward function using the optimal policy, so it relies on the reference policy. So here the reference policy refers to the policy that is being used to generate those two answers to be labeled to be compared. Okay, so in summary, so all those existing, most of those existing RLHF algorithms, they suffer from certain type of model misspecification. So basically, for both PPO and DPO-based algorithms, so first they suffer from misspecification of the preference model. So this is because they all rely on the BT model assumption. So if the BT model assumption is incorrect, then the estimated optimal policy is no longer optimal. And even when the preference model assumption, even when BT model assumption is correct, so the PPO-based algorithm still requires the correct specification of the reward model. And the DPO-based approach requires the correct specification of the reference class. And there are also some other like algorithms being proposed in the literature, but as you can see from this table, they also suffer from certain model misspecification. And finally, our proposed algorithm is referred to as DRPO, and one of its features is that it is robust to model misspecification. So it is, and in particular, as you can see from the table, it is robust to the misspecification in either like the reference policy or the reward model or reference policy. And next, just to give you like a summary of the contributions of our paper. So essentially, our methodologically, our major contribution is the development of this DRPO algorithm for LLM fine-tuning. And we also grouped some series of our algorithms. So there are two major properties of our proposed algorithm. One is the double robust property, and the other is the statistical efficient or like a sample efficient property, which I will also discuss later. And finally, we conduct numerical experiments to demonstrate the performance of our algorithm. And in particular, we consider the three benchmark data sets that are commonly used in the literature. And the reason why we choose those three data sets is that for the first data set, we found that the reference policy is likely to be misspecified. And for the second data set, we found the preference model assumption is likely to be misspecified. And the third data set is like a simulation data. And for this data set, either the model can be misspecified. So these three data sets, they are well suited to illustrate like the performance of our proposed algorithms under different types of model misspecifications. And next, I just want to give you a quick introduction of our proposal. So our main idea is to apply like those double robust methods to the application of the LLMs. So for those of you that are not familiar with double robust methods, so it is like a very classical statistical methods which originate from the missing data and causal inference literature. Suppose to better illustrate those methods, let's consider the problem of like estimating the average treatment effect in causal inference. So suppose we have like two treatments for a patient, a new treatment and the old treatment. Then basically the average treatment effect is defined as like the difference in the outcome between those two treatments. So that's the definition of the average treatment effect in causal inference. Now, in order to estimate those ATE, what those double robust methods do is that they will estimate two models based on the data. So the first model is like a propensity score model for treatment assignment mechanism. So basically for each patient, like what is the probability of assigning the new treatment and what is the probability of assigning the old treatment? So that's the meaning, that's the interpretation of the propensity score model. Now, if you think about this model is very similar to like the reference policy that I discussed earlier in large language models. And the second model is like an outcome regression model to model like how the patient outcome looks like after if they like take a particular treatment. And again, if you think about the interpretation of those outcome regression model, it is very similar to like the reward model that I have just mentioned in ELLIS. So what those double-robust methods do is that they estimate both models from the data. And then they use both models to construct the AT estimator. And it turns out that the consistency of the AT estimator only requires one of the model to be correct. So as long as like either the propensity score model or the outcome regression model is correctly specified, then the resulting AT estimator is consistent. And in addition, when both models are correct, then the resulting estimator becomes like a semi-dimensionally efficient. So this is a statistical property, which basically means that the estimator achieves the smallest mean square error among like a large class of estimators. And due to these nice theoretical properties of those double robust methods, these double robust methods they were later extensively studied and extended to like a wide range of problems. So including like dynamic treatment regimes, and of course, learning and evaluation in the machine learning literature. And in 2018, Victor and his co-authors introduced like the famous double machine learning paper, which extends the idea to also machine learning. And there are also extensions of those double robust methods to like conditional independence testing and to reinforcement learning. So as I have mentioned earlier, so essentially the main idea behind our proposal is to apply those double robust methods to the application of LLMs. And this figure basically summarizes our procedure. So essentially, so similar to like what previous work does. So for each of the question, we will have like suppose we will have like for instance LLM, a base LLM to give like two responses. And then we pass those two responses to a human expert. And then, very similar to those double robust methods, we estimate like two models from the data. So the first model is the reference policy, which basically describes like how those responses they were generated. And the second model is like the preference model, which basically models like the human context. So we estimate two models, and for each model, it can either be misspecified or it can be correctly specified. And because of that, we have like a total of 4 combinations. So there are 2 models in total, and for each model, it can either be correctly specified or misspecified. So this gives you the 4 combinations. And among those 4 combinations, so the first 3, so as long as like one of the model is correctly specified, then it guarantees that our estimated policy is optimal. So when like both models they are misspecified, then it gives us like a suboptimal policy. But that's the main idea behind our procedure. Now to give you some more details. So essentially what we did is that first we consider the task of preference evaluation. So basically for each of the target policy pi, we evaluate its like total preference. So here the total preference is defined using this equation. So it basically compares this target policy against the reference policy to see like how what is the percentage that the response being produced by this target policy will be preferred over those produced by the reference policy. So it's basically comparing the target policy over the reference policy. And we use like those double robust methods to estimate 2 models and to construct like the resulting double robust and semi-dimensionally efficient estimator for this total preference. And for each target policy pi, we can have such like a total preference estimator. And then we basically like solve this optimization problem to maximize to search for the optimizer that maximizes this total preference subjected to some like fail regularization. So that's the basic formulation of our algorithm. And we conduct some numerical experiments to evaluate the performance of our proposal. So this figure basically shows you like the mean square error of our preference evaluation estimator. So you can see that here there were 4 lines. There were 4 lines. So basically, we consider 4 combinations. So as I mentioned, like we estimate 2 models, and for each of the model, you can either be correctly specified or misspecified. So this gives you a total of like 4 different settings. And you can see that among those 4 lines, so firstly, the red line where both models they are misspecified, it achieves like the largest mean square error. It achieves the largest mean square error. And for the rest of the 3 lines, the mean square error is much smaller. The mean square errors are much smaller. So this partly verifies like the double robustness property. So basically, as long as like one of the model is correctly specified, then the estimator will produce like a much smaller mean square error. And secondly, so the blue line visualizes the mean square error where both models is correctly specified. And you can see that where both models is correctly specified, it achieves the smallest mean square error. And this partly verifies like the sample efficiency, the semi-parametric efficiency property. And we also compare our proposed ERPO algorithm against the like various existing baselines on like 2 benchmark data sets. And here the numbers reported here corresponds to the win rate. So it's basically like comparing our proposed algorithm against like those baseline algorithms. So what we did is that on the testing data set, we for each of the questions in the test data set, we asked like both our proposed algorithm and each of those baseline models to produce the response. And then we pass those response to the GPT to ask for preference, like basically among those 2 responses, like which one is being preferred by the GPT. And then we average over those preferences to get the win rate. So basically, if the win rate is over 50%, so this means that the response produced by our model has like a higher chance to be preferred over the baseline. So if you look at the first table, so we can see that our algorithm achieves like a win rate consistently larger than like 50%. It has a better performance when applied to this data set. And for the table on the right, so that's the win rate of like those different algorithms compared against the supervised learning policy on the HH data set. So you can see that in this case, the win rate of our model is like 86%. It is better than some of those existing algorithms, and it is also similar to like some baseline or slightly worse compared to some of the baseline algorithms. And finally, I just want to give you a summary of the theoretical properties of our proposal. So we basically studied like the double robust property and the semi-parametric efficiency property of our proposal. So just to give you more details. So for preference evaluation, we established like a double robust property, which means that our proposed the mean square error, for instance, the mean square error of our proposed estimate indicates to 0 when either like the reference policy or preference model is correctly specified. And when both models they are approximately correct, then you can show that the proposed estimate it achieves like the efficiency bound, which is like the smallest possible mean square error that one can hope for estimating this total preference. And then in terms of preference optimization, we also show the double robustness property, which basically states that the performance gap of our proposed policy it decreases to 0. So our estimated policy is like in some sense very close to the optimal policy when either the reference policy or the reference model is correctly specified. And if you look at the last bullet point, so we further establish like the sub-optimality gap of our proposed algorithm against like the first 2 type of baseline algorithms, the PPO and the DPO baseline algorithm that I mentioned earlier. So you can see that the key difference, I think that for those two baseline algorithms, so the estimation error of the reward function and of the reference policy appears contribute like linearly to their suboptimality gap. But for our proposed algorithm, like if those errors they contribute like in a second order, those errors they contribute in a second order appears as a product. And because of that, when both errors are small, if you multiply them together, it will be small. So that's why like our proposed algorithm can achieve like a better performance compared to like those two baseline algorithms in theory. So that's the first project, and how many time?
15 more minutes.
Okay. And in the next like 15 minutes, I will talk about the second project, which is about adaptive detection of LLM generated text. So for the second project, the problem is very simple. So basically, we aim to distinguish like given a text, whether it is generated by large language models or it is generated by human beings. So just to give you an example, so here there are two like paragraphs. If you look at like the novel, the sci-fi, the three-body problem. So there's like a hypothesis, which is about like the dark forest hypothesis or dark forest theory. And basically here are like two paragraphs about the dark forest hypothesis. So one of them is generated by large language models, and one of them is generated by like human beings. And you can make a guess like which one is generated by LLMs and which one is generated by humans. I think it's not that complicated. So basically, the first paragraph is taken from the three-body novel written by Cixin, and the second paragraph is what I get by prompting the ChatGPT to produce to rephrase, to rewrite the first paragraph. But I think the problem is very clear. So basically, in the second project, what we did is to consider like this classification problem. Okay? So given a text, we want to distinguish like whether it is generated by a human LLM or it is generated by human beings. Okay? So that's our objective. Now, next, I just want to give you a review of the related works. So in the recent like 2 to 3 years, there were like a lot of works being developed on such type of problem. And these works, these algorithms, they can be roughly divided into like three categories. So the first category of algorithm is referred to as statistics-based detection. So essentially, what it does is that so it will construct a statistic based on the target. So suppose if you want to detect like whether the text is generated by ChatGPT or not, then it uses like some information from ChatGPT to construct a statistic. And then given this statistic, it will determine like whether the text is generated by ChatGPT or written by human beings. So for instance, if the statistics is larger than some threshold, if the value of this statistic is larger than some threshold, then it is generated by say or a large language model. So that's those statistics-based detector. And the second class of detector is referred to as like a machine learning-based detector. So essentially, what it does is that it treats this problem as a classification problem. And then it like extracts like a human data set available on the internet. And then it also asks LLM to like rewrite those human data set to produce like an LLM also text. And then it treats this problem as a classification problem. So once we have those two different types of data set, we can basically train a classifier. We can apply like machine learning algorithms to train a classifier to achieve this objective. So that's the second type of algorithms referred to as ML-based detectors. And the third type of detector is like those watermarking based detector. So for these algorithms, we assume like we have access to the LLM. So basically, we can modify the LLM. We can build our own. We can make some modifications to those LLMs. And so what this procedure does is that it will embed some like small signals, referred to as watermarks, when generating text based on these LLMs. And then like it will based on the text, it will detect whether the text contains like those small signals, contains those watermarks. So that's the third category, watermarking based detector. And for our detector, so that's a visualization of our detector. So it's more closely related to like the first type of classifiers. It is more related to the first type of detectors. So basically, our proposal is also based on these statistics-based detector. So we use our procedure is built upon those statistics-based detector. But we also like it is also similar like to those machine learning based detector in the sense that we use those data to enhance the performance of those statistics to improve these statistics to achieve better classification accuracy. Okay. So that's our that's the main illustration of our proposal. Any questions at this stage? So as I have mentioned earlier, so our proposal is built upon those statistics-based detector, and in particular, it is based on this fast detect GP proposed by our ECSO last year. So essentially, for those statistics-based detector, what it does is that it assumes it has like the target LM's next token prediction probability. So here, QT indicates the probability distribution function. So given all previous T-1 tokens, like what is the probability of the next token? What is the probability of next token? So we use QT to denote this conditional probability distribution. And for detectors such as fast GP, it assumes like we have such probabilities. So suppose if we want to detect like whether a text is generated by ChatGPT, we assume we need to have like those next token prediction probabilities from the GPT. And the main idea behind this proposal is that they found empirically they found that this probability they will be different when evaluate the human and machine generated text. And because of that, we can basically use these probabilities to construct a statistic and then use this statistic for the purpose of classification. So that's the idea behind this algorithm. And more specifically, so that's the statistical measure being used in the paper. Now, if you look at this equation, so basically the first equation, the first term in the numerator corresponds to the log probabilities that I have mentioned earlier. It corresponds to the log probabilities that I mentioned earlier. And the second term in the denominator and in the numerator and the denominator, they basically corresponds to like some centering term. They basically corresponds to some centering term and like some virus term to standardize these log probabilities. So the main idea is to use those log probabilities for detection, but they apply some standardization procedures to normalize it to have like zero mean and like unique variance. And if you look at this figure, so this figure basically shows you like the distribution of this statistic when applied to like human generated and to human and machine generated text. And you can see that clearly the distribution they are different. Like LLM generated text, it tends to have like a larger value of this statistic compared to human generated text. And because of that, basically they use such statistical measure for the purpose of classification. And if this statistical measure is larger than some threshold, then they assume then they conclude that the text is generated by the target LLM. So that's the main idea behind fast detect GPT. And if you are familiar with like a probability of statistical theory, so basically if you look at the numerator of this statistical measure, so the numerator forms a which is like a particular statistical process. And later what we did is that there were like many nice statistical properties of martingales, and later basically we will use these properties to improve the performance of fast detect GPT. So this slide shows you our proposed statistical measure. So again, on the first equation, so this is the fast detect GPT statistic that I have just mentioned earlier. And if you look at the second bullet point, so that's our proposed statistic. So it's very similar. So the only difference I think that we apply like a one-dimensional transformation function to this above probabilities. So denoted by W. So that's the main difference. That's the main difference. And those W's, they will be then effectively from the data later. I will introduce the procedure later to improve the detection accuracy of the statistic. But that's the main idea of our procedure. Is very simple. Just to apply like a one-dimensional transformation function to the law of probabilities to enhance the detection performance. And why shall we use such a one-dimensional transformation function? Well, firstly, here are some like numerical experiments which visualizes the statistical measure of like fast detect GPT and our proposed detector, which is referred to as adder detect GPT. And so basically, you can see that all these, most of those statistics, they are positive. So they basically measure like the difference of the statistical measure between the LM written text and the human written text. So if the difference is larger, then it is more likely to be detected. And then you can see that compare adder detect GPT, our proposed adder detect GPT against the fast detect GPT, like our statistical measure is likely to be large. So that's the benefits from our in vitro studies. And we also conduct some simple theoretical analysis. So basically, this is like a kingdom of bit example in our paper. So basically, we consider like a very simple scenario, like where each person, suppose like there's a kingdom of bits, where each person only speaks like 2 tokens. They speak in 2 tokens. And suppose like one day there's like a malicious wizard which creates like those synthetic human beings. So those synthetic human beings, they look very similar to the ordinary people, but they speak like a different language, So you cannot tell, you are not able to tell like whether it is ordinary human being or like it is a synthetic citizen based on their appearance. But you can only detect them based on the language they spoke. And then what we have found out is that suppose like those synthetic citizens created by the wizard, so suppose they spoke like ID, so which is like a very simple which is like a very simple scenario, And when those when each token's probability is close to 0.05, then existing detectors such as fast detect GPT, they will fail to distinguish between like human spoken language and from those synthetic citizens. So regardless of how different those P and Q are. But to the contrary, suppose if we with like a properly learn the function W, our proposed adder detect GPT can consistently detect those 2 different languages. So that's a very simple like analytical example to illustrate the benefits of using this link function to applying this one-dimensional transformation function. So now I have discussed like the motivation of using a one-dimensional transformation function, and the next few slides basically gives you an introduction of like how to adaptively learn this link function from the data. And due to the time limit, I guess I will just be quick. So the main idea here is that since we consider the classification problem, there are very natural criteria to consider. It's like the corresponding AUC the area under the tree, under the curve of this detector. So our objective is basically to identify like the W that maximizes the AUC. And this is equivalent to say that for each fixed level of false negative rate, we aim to find a W that maximizes its true negative rate. Okay? And our proposal consists of the following three steps. So basically, for the first step, we for each alpha, where alpha corresponds to the level of the false negative rate. So we identify the threshold. We identify the classification threshold so that the FNR of this classifier is controlled at the level of. Okay? And then once given this threshold, we identify like the true the true negative rate of this classifier or its lower bound. And then basically we optimize the bound to maximize this TNR or its lower bound. And here the major technical tool is like the multinomial central limit series of that which is like a very classical result in statistics and the probability series. So as I have mentioned earlier, like those statistical measures, they are martingale. They are basically form a martingale, and because of that, you can use this multinomial central limit series and apply normal approximation to identify like the classification threshold and to identify the post-form expression of the team to be maximized later. And due to the time limit, I will just skip these procedures, and here are some simulation results. So basically, the numbers here corresponds to like the AUCs of each classifier, the AUCs of each classifier, and you can see that our proposed added factor GP achieves like the largest AUC compared to like existing a range of existing methods, including like fast GP and some other baseline methods. And also we consider settings for detection of like GP type of models, and again, like our proposed added GP achieves larger AUCs in most scenarios. And finally, we also have like some theoretical guarantees for procedure. And again, since we consider like the classification problem, so some very natural measure to consider is like the true negative rate, the false positive rate, the false negative rate, and the true positive rate of the corresponding classifier, and we established like the corresponding theoretical properties of our detector. So that's all for my talk. And again, I thank you very much for having me here, and thank you for coming.